So question 11 then from paper 2, the 2023 advanced higher, 6 marks for, it's a related rates of change question. How does the rate of change of one variable affect the rate of change of another one? So ultimately you've got a chain rule going on there, a chain of differentials. What does it say? You've got this water container, this conical water container, so it gives you the volume of a cone. And you have to show first of all for this particular one, how you could express V solely in terms of H. So you've got to eliminate R in other words. Well, that'll just be a similar triangle, won't it? Because the radius would be 90 if that's 180, and that height's 150. So that gives you a connection between the radius and the height. So what you can say there is the radius, the ratio of the radius to the height is 90 to 150. So that's 3/5. Which means that the radius is 3/5 of the height. Right, now you just put that in then. So that volume will be 1/3 of pi times 3/5 of the height squared times the height. Now just take all the numbers out then. That was a 5 under there. Well, that 3 will knock out one of them, so left with a 3 and a 25. So that's 3 pi upon 25 and then h cubed. Okay, they had the line going under it all, but I've just left it like that. Now, part B it says, now water gets poured into that at a constant rate. So there's a change in volume. So that means dV by dt is 10 litres. Well, the rest is going to be centimetres. So that's 10,000 centimetres per second, centimetres cubed per second. If that's the case, if it's getting poured in at 10 litres per second, how fast is it filling? How fast is the height change when it's up at 125? So you want the rate of change. You're looking for dH by dt at h equals 125. Well, you just start constructing a little chain rule. You just shugle the differentials about. If you want dH by dt, which is what you want ultimately, how could you construct that? Well, I could get that from a dH by a dV, because I've got a connection between them here, times a dV by a dt, which I've got here. So it's just a case of getting this. You get that from that, because that's a function, v is a function of h. So I've got that. So I've got dV by dt is going to be 3 times that, so that's 9 pi upon 25 h squared. So that's it. That's a dH. So that's it upside down. So just turn it upside down. So that'll be a 25 over a 9 pi h squared times dV by dt. I should have left myself more room here. But I'm just going to put in the numbers now anyway. So what have I got? I've got 25 times, now what was dV by dt? 10,000 over 9 pi times, and it's at 125 squared. And those units are all fine, aren't they? Because that's centimetres cubed per second, that's centimetres squared, so the final answer will be just centimetres per second. So putting that in means that the rate at which the height is increasing at 125 centimetres should be 0.5658 and so on, and that's centimetres per second. So I don't know how they want that rounded off. 0.57 will I say, centimetres per second. Number 12 then, from paper 2, the 2023 advanced higher, 5 marks for proof by induction. Prove that for all positive integers n, that this summation result is actually true. Well, the first stage would be, is it true at the very start? Is it true for n equals 1? Well, so n equals 1, what have we got? So you just got to check if the two parts will give the same answer. Well, that going from 1 to 1 is just that first term. So that left hand side would just be 2 to the 1 minus 1 times 1. 2 to the 0 is 1, 1 ones are 1, so that comes to 1. Right hand side, 2 to the 1 times 1 minus 1, well that knocks all of that out, plus 1, also comes to 1. Right, so it does work. It works at the very beginning. So from that you can say, that means it's true for n equals 1. We need that. Forgot to say left hand side equals right hand side first. Just put them in. Now we check if the link works. So let's just, what you do is you assume it's true somewhere further on for n equals some random number k. Now if that's the case, that means that going from r equals 1 to k of 2 to the r minus 1 r should produce the result 2 to the k minus 1 plus 1. We don't know if that's true. That was true, we don't know if that's true. So this is the inductive hypothesis. This is what you're going to be using. So we're just assuming that that did actually work at that point. Now we're going to test. Consider n equals k plus 1. You're not going to consider it using this formula. You're just going to consider it from basic arithmetic. That means that sigma r equals 1 of k plus 1 of that whole thing should be r equals 1 to k of 2 to the r minus 1 r minus, rather plus, just the extra term that this needs. To go from k to k plus 1, you just add one more term. So that one term would be the term with k plus 1 in it. That was the final value of r. So that expression for the terms you're adding up says 2 of, and that'll be a k plus 1 minus 1 times a k plus 1. Now that's got nothing to do with the rest of it. That's just a simple piece of algebra. But this bit is, now I'm going to call this in, this if bit. So for this part here, we're going to assume we're going to call in 1 and say that's, this part comes to 2k times k minus 1 plus 1. And that's that's just k then, isn't it? Times k plus 1. That was using the inductive hypothesis, calling it in. Now we're just going to tidy this up and see if it gives you the result you would expect if n was a k plus 1, if you can make it look like this. Well, I've got a common factor, I know the 1's not in, throwing that out, I've got a common factor of 2 to the k. And that would be a k minus 1 for that term, and a k plus 1 for that term. And then I know I've got that separate 1. So that's 2k. So that's 2 to the power k times 2k plus 1. That 2 can join this and bump that up to a k plus 1. We're getting there. But unfortunately, it just leaves a k plus a 1. Notice that. However, a wee bit of arithmetical jiggery-pokery can turn that into exactly what you want, because that's the same as k plus 1 with 1 taken off. Now that looks exactly like that does if that n was a k plus 1. So I can say equals the required result, for n equals k plus 1. Now it's the big spiel, because that says it worked. That says, assuming that that was true, that worked. So now we just have to write all this out. True for n equals k meant it was true for n equals k plus 1. And since it was true for n equals 1, that meant by induction it was true for all n members of the positive integers. Now, it could have been fancy and said by mathematical induction, but that's implied in the context.